We keep throwing around the term half-life, and now is a good time as any to put some math to it. Looking at half-life, as we might expect, we see that one half-life cuts things in half, two half-lives cut things in fourths. I think I got the picture. How about n over n naught is equal to 1/2 to the tau, where n is the number of atoms you have now, n sub naught is the number you started with, and tau is the number of half-lives. Next, let's change tau to an expression that explicitly shows the number of half-lives. I have n over n naught is equal to 1/2 t divided by t 1/2, where t is the time and t 1/2 is the half-life. Well, this is true, but it's awkward. It's usually changed to n over n naught is equal to e to the minus 0.693 times time divided by the half-life, or is equal to t to the minus lambda t. And finally, the form you see it in the textbooks, n equals n naught e to the minus lambda t, where lambda is the decay constant and is equal to 0.693 divided by the half-life. In words, lambda is the probability that an atom will decay in a second and has the units of inverse seconds. Now let's work a problem. Starting with 500 atoms that have a half-life of 55 seconds, how many are left at 5 minutes? Get your pencil and paper and do it again. I get 11.41 atoms. And just between you and me, I think it's kind of hard to have 0.41 atoms. What's wrong with our equation? Nothing is wrong with our equation. In fact, our equation is better than reality. What the equation says is, if you repeat this experiment many, many times, on average, you will have 11.41 atoms left after 5 minutes. This is somewhat the same as the average couple in the United States having 2.13 kids, or 2.42 neutrons emitted during fission. The equation describes the expected value, to use the statistical term. There's another wrinkle because it's statistical. Our formula gives the average value. In real life, if you have a small number of atoms, the odds that you will get exactly the answer given by the formula, even if it's a whole number, is small. Well, how can this be? Let's think of flipping coins for a minute. If you flip a fair coin 500 times, how many heads do you expect? 250, right? The odds that you get exactly 250 heads when you flip a coin 500 times is only 3.566%. To be clear, if you repeated this experiment many times, your average number of heads will get closer and closer to 250. About half the trials higher and about half lower, just as we predicted. It's just that we don't get 250 each time. Leaving statistics behind for a minute, let's return to decay, radioactivity, and radiation, and I'll show you some nifty things we can do with our decay constant.